Good evening, sir.
Okay. Yes. Good evening, people. Good evening. And so we have completed the journey from classical to quantum, and today we are starting with the proper quantum mechanics. That's it. The first chapter that we are going to name is just okay, heading people, mathematics for quantum mechanics, MFQM. Okay. Now listen, this chapter is again not exclusively mentioned in exam where you have to learn mathematics for quantum, but the point is in order to understand anything forward, it's important that first I teach you the language, the ABCD of it and everything. So today's lecture you can consider is literally like the ABCD of what we need later on. Okay. Exclusively from today's lecture, something may or may not be asked. Okay, but like I said, it could be a subset of a larger question. Whatever we are going to learn today is going to be a subset of a larger question. Okay, so you don't have to keep yourself pressurized all the time to literally ensure that. I mean, it is not supposed to be a heavy class, people. It is just going to be a very fundamental class. Maybe things might be a bit new to you. I'm not sure how confident you have been during your quantum, so I will try to ensure that you understand things decently, but still keep asking questions if you have any. We'll just get started without wasting time now. So anyway, so the first thing that I want us to learn in mathematics for mathematics today is linear vector space. People, please give it. Linear vector space, popularly known as LVS. So just write it with me. Okay, people, a space of vectors. A space of vectors. Any vectors you can write down, like alpha, beta, gamma, delta, whatever you want to use. But usually what we do is we use capital Greek letters, and that too usually revolving around psi, phi, chi, and it goes on. These are our favorite vectors when it comes to quantum mechanics, people. Okay, no specific reason for such. Just that we have used alpha, beta, gamma for constants and for different phases already in different chapters. In quantum, usually we deal with the capital vectors psi, phi, and chi. Okay, and it goes on. Belonging to a vector space, V. You can call this vector space V. Okay, which obeys. So whatever vectors you have, people, in that particular space, you can denote it by A vector, B vector. Notation is not a compulsion, people. Notations are arbitrary. These are our favorite letters that we use. Otherwise, we can use any. Okay. So the point is, vectors which obeys a certain kind of rules are known as linear vector space. Now, what are the rules that it must obey? So which obeys? Number one, the first, sum of any two vectors will give another vector. But important is what people listen. So sum of two, obviously vector plus vector, it has to give you a vector, but that particular vector, the third vector, must belong to the same space. Will give another vector belonging to same space. It cannot go out of the space. That's important. So if I give you, let's say, suppose a region. In region, suppose you have a value 2. Suppose you have a vector A basically. Suppose you have another vector B. If you add A and B, suppose you get another vector C. C must lie in that space. It cannot go out of that particular space. Simple. So whatever boundary conditions you have met, basically they should obey that boundary conditions. That's right. Second important rule is scalar multiple of the vector. Scalar multiple of the vector. Scalar multiple means multiply these vector with any scalar number, like 2 psi, pi psi, 3 psi, a psi, b psi, whatever. 2, 3, pi, a, b. These are scalars. Okay. Scalar multiple of vector gives us another vector. Obviously, if you multiply vector with scalar, it gives you a vector once again. Now. So gives you another vector. Gives us another vector. Again, belonging to same space. That's important. Belonging to same space. It cannot go out of the space. That's it. Make a note of this much. So as far as all the vectors that you are speaking of, they're obeying these two rules, people. You can say it's a linear vector space. It's a linear vector space. By the way, pronunciation is psi. This is psi. This is phi, and this is chi. Chi. Psi, phi, and chi. In some another parallel universe, somebody would have pronounced it as C, P, and Chi. Okay, but we will pronounce it as psi, phi, and chi. Then people copied?
Yes.
Okay. So basically, it's something like if you add, let's say, psi plus phi, you should get another vector, like you should get chi or any other vector, but that vector is basically belonging to that particular space. Okay. Similarly, if suppose you multiply one of the vector with scalar multiple, you should get another vector belonging to same space. You can get chi, you can get phi, you can get any other vector, A vector, B vector, but it should belong to the same space. That's right. Okay. Addition of two vectors should give you a vector belonging to same space. Multiplication with a scalar, two vectors should give you a vector belonging to same space. Two important rules. Next. By the way, remember when you say A is a scalar, sir, which kind of a scalar? Like, should it be number variable? It could be any number variable, we don't care. In fact, it could also be a complex number also. Scalar has no boundaries, people. It could also be a complex number. So you can say scalar belonging to complex number, doesn't matter. Okay, complex is the highest now. Like you have got natural numbers, you have got whole numbers, you have got integers, you have got rational numbers, you have got real numbers, but all of them at the end are subset of complex numbers. Complex are the largest set of numbers. It includes everything. So belonging to complex numbers. Okay, next. Now let's define linear operator, people. Please give heading linear operator. Okay. So to start with, a linear operator is basically that operator which follows. There are two simple rules. So you can denote the operator with anything now. I'm using R cap right now. You can use any operator. So operator means what? Anything which can change the function. Like derivative is an operator, people. Integration is an operator. Matrix is an operator. When you apply matrix on something, it changes the coefficient of it now. Eigenvalues, eigenvectors, whatever. So eigenoperators you have learned. So all of these are operators. Okay. So that operator which follows, simple. Number one, R cap. If you apply the operator equal on U plus V, then it should be always equal to individual of R cap U plus R cap. R cap of U plus V should be equal to R cap U plus R cap. If I think, but sir, this is always true. No, it's not always true. We will check it as soon as we take an example. It should obey this. Okay. Similarly, R cap into, let's say there is a scalar multiple of U. You can throw scalar multiple outside. It should be R cap of U. It should follow these two rules. If you are thinking, but sir, logically, don't you think it should always obey? No, it's not necessary. It will always obey. We will take some examples. Don't worry. That operator which follows these rules. So basically, this is distributive rule. R cap of U plus V. It should be R cap U plus R cap V. And this is a scalar multiple rule only. If you have a constant, if you have a scalar, you can throw the scalar outside. It should obey these rules. Okay. Let's directly take a question and understand. U and V are functions. U and V are functions like x and y. Okay. So let's check people. Here we go. Let's take an example. So suppose they have given us that there is an operator which obeys a relationship. Suppose if you apply that operator C cap on a function u, you get 2 into u. They have given that there is an operator C cap. When you apply it on a function u, you get 2u people. Like, or you connect C cap on a function f, it gives you 2f, whatever. Now the question is this a linear operator or not? In exam, they can give you an MSQ. Which of the following is or are linear operators? There can be 4 options and you have to mark the correct ones. Okay. So let's work on this. So what is the first condition it should obey, people? The first condition it should obey is if we have u plus v, it should be equal to C cap u plus C cap v. It should be equal to this. Correct? This should be obeyed. So let's check this. Okay. Let's check this. So let's start with LHS. Okay. So I want to calculate C cap of u plus v. Okay. C cap of u is twice of u. So C cap of u plus v is like you have replaced u people. You have replaced u with u plus v. So here also, wait, hang on. So you have replaced u with u plus v now. Answer should be replace u with u plus v. I repeat, answer should be replace u with u plus v. It's like C cap of capital U. So answer will be what? 2 of u now. C cap of capital U, answer will be 2 of u. So C cap of u plus v, answer will be 2 of u plus v. I hope you understood this. Tell me if not. So this is the LHS value, people. You can write 2u plus 2v. This is the LHS value. Let's check RHS, people. What is RHS? C cap u plus C cap v. C cap u plus C cap v. Okay, let's apply. So C cap u is 2u. Okay. So replace u with me. Replace u with me. C cap v is 2v. Outstanding. These two are matching. LHS and RHS are equal. LHS and RHS are equal. It means the first property is obeyed, people. Whatever was the first property is obeyed. One is obeyed. Now we have to check the second one, people. Now we have to check the second one. Let's apply on the second one. What is the second property that it should obey? When you apply the operator on a scalar multiple of the function, you should get scalar multiple outside into the operator. Let's check with LHS. So what do we have? C cap of AU. Okay, simple. Replace u with AU. So here also you will replace u with AU. Let's do that. Okay. So I'm going to do C cap u is 2u now. So C cap replace u with AU, like I said, and here also answer will be replace u with AU. So this is 2 of AU, or you can say 2AU. Clear? Let's check RHS. What is RHS? C cap. Here, RHS is A into C cap u. A into C cap u. Okay. A into what is C cap u? C cap u is 2u now. So you got 2AU people. This is also 2AU. This is also 2AU. Again, LHS is equal to RHS. You can simply see that once again, second property is also obeyed. Second property is also obeyed. Since both the properties are obeyed, you can say this is a linear operator. Make a note. So given operator is a linear operator. Given operator is a linear operator. You're checking that, okay? Tell me if you have any questions. Don't hesitate. So C cap u is 2u. C cap u is 2u. U is basically u plus v this side. Okay, that's it. C cap u is 2u. Okay, so C cap u is 2u. U is AU this side.
Yes, sir.
Okay. Let's take another example. Tell me if you're writing. Okay, so right now, since both the properties are obeyed, given operator is a linear operator. Right now, since both the properties are obeyed, given operator is a linear operator. Since both the properties are obeyed, given operator is a linear operator. Okay, let's take another example. Suppose they have given us C cap u is u cube. There is an operator when you apply on a function such that you get u cube people. Okay, so the question is now is this a linear operator or not? Let's check. Let's start with the first property. What is the first property? C cap of u plus v should be equal to C cap of u plus C cap of v. Let's check. Okay, so LHS people. LHS. C cap of u plus v. So this is C cap u people. C cap u is u cube. So C cap of u is u cube, right? U is u plus v this time. Cube. U plus v the whole cube. What is a plus v the whole cube? A cube plus 3a square v plus 3ab square plus b cube. I hope you remember this formula. Next, let's check RHS people. Okay, RHS is C cap u plus C cap v. C cap u plus C cap v. What do we have? C cap u is u cube. Okay, C cap v will be v cube. Are they matching now?
No, sir.
That's it. This is not a linear operator. Not a linear operator. Make a note, please. For your satisfaction, you can also check the second property. This is the first property. You can also check the second. Anyway, if one property is obeyed and the other is not obeyed, it is anyway not a linear operator. In order to be linear operator, it should obey both of the properties. But for practice, we can check the second one. It's already not a linear operator, but we can check the second one. Okay. Let's check. Tell me if you're writing these. Here we go. Let's check the second. So what do we have? C cap of AU, that should be equal to A into C cap. Okay. Let's check with LHS. C cap of AU. What do we have? C cap U is U cap, U cube people. C cap U is U cube. U is right now AU, no? So AU cube. So this is A cube, U cube people. Let's check RHS. RHS is A into C cap U. A into C cap U. So this is A into, what is C cap U? U cube. C cap U is U cube. Are they matching? No. Even the second property is not matching people. No match. Okay. Anyway, so both the properties are not matching. This is just for our understanding. It's not a linear operator.
सर
बोलो
सर एक डाउट है सर
बोलो
सर एड एंगल मेटेरियल में क्वेश्चन है सर बोल रहा हूं मैं
हाँ किस रिलेटेड
ये वो सर लेमडा से कल पढ़ाया था ना हमने
हाँ हाँ ओके हाँ ठीक है पूछो
डिटरमाइन द वेवलेंथ ऑफ द k अल्फा एक्स-रे लाइन और मोलिवेटनम z इक्वल टू 42 है इसके लिए
ओके z 42 दिया है और पूछा है लैम्डा निकालना है
k अल्फा है
ओके अल्फा का
सर यहां पर आंसर है सर z इक्वल टू z इफेक्टिव दे रखा है z -1
z -1
सर के लिए z -1 होता है ना
हाँ k अल्फा के लिए z -1 है वी लर्न ना मोसलेस लॉ है ना लाइन में सीरीज यूज मत करो यहां k अल्फा के बीटा लिखा मोसलेस लॉ
ओके सर
ठीक है बस कर
खत्म
ठीक है Okay. K alpha K beta रहेगा तो most for use करना है. And if at all they like Lyman-Barber passes, then exclusively use that particular formula. The thing is, in your school and high school, when you are taught this Lyman-Barber passes series people for the very first time, they don't talk about effective Z and everything, because obviously for young students it would be very difficult to grasp all those concepts. And hence in Lyman-Barber you don't talk about the effective Z. But if they specifically mention about K alpha, like K beta line and everything, you have to use most for. Okay. So then people, we can take another example here. Suppose we have got C cap U is, let's say, du by dx. Let's check. It's basically derivative. It's a derivative. Okay. So let's check. What is the first property, people? The first property is C cap of U plus V. It must be C cap U plus C cap V. Let's check. So let's start with LHS. So we have C cap of U plus V. So C cap U is du by dx. C cap of U plus V. This will be d by dx of U plus V. We can split them. This is du by dx plus dd by dx. Okay. Let's check RHS. This is C cap U plus C cap V. C cap U is du by dx. C cap V is also dd by dx. Absolutely. The first property is matching, people. First property is matching. Take a look. Okay. Tell me, let's check the second property. Okay, tell me if you're writing. Okay, second property tells us that C cap into AU should be K into C cap U. Let's start with LHS. LHS is C cap into AU. So C cap U is du by dx. C cap U is du by dx. So this is d by dx. So what is U this time? AU, people. I can throw A outside, du by dx. Let's check RHS. RHS is A into C cap U. A into C cap U. So this is A into C cap U is du by dx. Absolutely, it's matching again. Both the properties are satisfied. Given operator, derivative is a linear operator. People. Simple. Derivative is a linear operator. Both the properties are absolutely matching. Clear, everyone? Given operator is a linear operator. So I hope linear vector space, linear operator, this concept is clear. If at all by any chance they ask a question on this, you'll be able to do it. Proceed ahead. Next. Now, there are certain rules which we want to learn for linear vector space. So linear vector space, even though we define two things, that there are conditions that if you add two vectors, it should give a third vector in the same space. If you multiply with scalar, it should give us a vector again in the same space. There are certain rules also. Number one, let's talk about addition rules. Very quickly, addition rules. Okay. So first of all, before defining the rules, let me just define initially. Suppose I've got three vectors, psi1, psi2, and psi3. You can also use psi, phi, chi. I don't care, whatever you want to use. Any vector. Okay, I'm going to 7 psi, psi3. Suppose they belong to a linear vector space D. These are linear vector space, right? Okay. So first of all, it obeys the first law, which is known as the associativity law. Associativity law. You have done these things, I'm sure, in maths, in physics, both of them. So which is basically psi1 plus psi2 plus psi3 is equal to psi1 plus psi2 plus psi3. Okay. The point is brackets can be shuffled. It doesn't matter if you add first and second, and then you add it with first, whatever answer you will get. First and second can be added, and even if you add later it with third, answers will match people. So order of addition is not important. When you say associativity, order of addition is not important. If you are thinking, sir, this is so silly, it's always valid. No, people, there are things in physics where order becomes important. Here, order of addition is not important, but there are things where order becomes important. For example, BODMAS itself. In mathematics, you know that bracket comes first, division, then multiplication, addition, and then subtraction. Okay, so order is important. Okay, in many cases. Anyway, so this is associativity. Next, then it also obeys. This is known as addition identity. Next thing we are learning is known as identity. Identity basically means what, people, that there should be an operator which will never affect your answer. So in addition, what should I add which will never affect my answer, people? If I give you a value x, what should I add to x? 0. It will never affect my answer. That's it. So psi plus 0 is 0 plus psi is psi. 0 is known as identity operator, basically. 0 is identity operator. Okay, so in addition, additive identity operator, to be more precise, additive identity operator. But right only you can tell what could be multiplicative identity operator. What should be multiplicative? One. Okay, so this is identity operator. Okay.
So what's the heading of this subsection?
No, nothing. We are still learning linear vector space, rules of linear vector space. So addition rules. Okay. Okay, next. Then we have inverse, people. Third case, tell me if you're writing now. Inverse. So inverse is basically we should add something or we should multiply something, that answer becomes 0. So obviously, what should we add to psi? It becomes 0. Minus psi. Okay. So psi plus minus psi, it gives us 0, or you can say minus psi plus psi, answer becomes 0, people, always. So minus psi is known as additive inverse.
Additive inverse.
Yes. Additive inverse. Okay. And then it should also obey the commutative property. Like your favorite one, a plus b is b plus a. Psi1 plus psi2 is equal to psi2 plus psi1. Again, if you are thinking, but sir, this is always valid. No, this is not always valid. For example, cross products, a cross b is not always equal to b cross a. A plus b is minus of b cross a. So no, commutative is not always necessarily equal. It depends what kind of relationship you are talking about. A dot b is b dot a. In dot product, commutative is fine. In cross product, commutative is not fine. Okay. Here, commutative properties are obeyed in linear vector space. So commutative, associative, additive inverse exist, and additive identity also exists, people. Next, so these are the 4 addition rules. Any linear vector space must obey. They must obey. Okay, proceeding ahead. Now let's talk about the multiplicative rules. Multiplication rules, which any linear vector space must obey. So again, before I start with, I want to define a couple of vectors. I want to define phi, I want to define psi. Both belong to linear vector space B. You can write psi1, psi2. You can write psi, xi, whatever you want to use, doesn't matter. And let's also define
additive inverse and 0 also belong to the same vector space, maybe.
Yes, I mean, these are scalars actually. So in vector space, we don't define them. However, you can say these are scalars. They can be complex numbers. So right now, if I want to say A and B, you will say they belong to any complex number. That's it. They are any scalars, so no problem. Okay. So A, B, we can say they belong to any complex number. Proceeding ahead. First property, distributive property. Distributive property, which is if you have a scalar psi plus phi, you can split them a psi plus a phi, just like linear operators basically. However, Very similarly, if you have two scalars multiplied into a vector, even this can also obey distributive law. You can write this as a psi plus b psi. These are silly things, people, but still, at times it becomes important to go through that much. Next, proceeding ahead. B, which is distributive law. Again, sorry, distributive is already there. They have written it down. This is not distributive. What is this then? It should be a b side bracket shifting. It is associative. They have written distributive, that's wrong. But okay. So a into b side, you can shift the brackets. A b into side doesn't affect your answer b. Okay. So multiply the side with a scalar, whatever result you get. Multiply that with again a scalar, whatever result you get. That will always be equal to first multiply the scalars and then multiply with the vector. Again, very silly, but okay. Next, proceeding ahead. Then obviously you already know the multiplicative identity. What is multiplicative identity? Identity means things remain same as it is. So it's 1. So psi into 1, it is 1 into psi, it is psi into 2. Multiplicative identity is 1. And multiplicative inverse?
1 by.
No. In inverse answer should become 0, no?
0, 0.
0. Psi into 0. This is 0 into psi. Answer is 0. 0 is multiplicative inverse. 0 is multiplicative inverse. Any questions? Anyone? Anyway.
सर एडिटिव इनवर्स में माइनस कर दे तो इन मल्टीप्लिकेटिव इनवर्स में 1 बाई होना चाहिए ना
But अगर तुम 1 by psi लिखोगे तो कैंसिल होकर 1 बचेगा ना. Inverse means you should get 0. Multiplicative inverse means you should get 0. If you are going to get 1, it won't be inverse. Matrix नहीं लगाना यहाँ. Matrix you have a into a inverse is the identity option. That's different. Okay. Next. Inverse means you should get the answer to be 0. So here, in addition, there is only one way to get the answer 0. That is by writing minus it. There is no other way. But here, you can get 0 if you multiply with 0. There is no other way to get 0. You cannot multiply by 1 by psi. In that case, you will get 1. So that too becomes different. That is what you call it. Matrix for inverse. Okay. Answer should be 0 basically. That's fine. Okay. But if you want to define, you can define that. It doesn't matter how to get 1. I'm not sure what you call that rule, but I mean this is absolutely fine. But no, actually we don't divide by wave functions. Vectors are not divisible. No? How can you write sine inverse? You cannot divide vectors. That's the first thing that you do. You either add, either subtract, either multiply. Have you ever learned 1 upon a vector? No, no. Vectors are non-divisible. You cannot divide the vectors. Okay. And hence, obviously, you don't write sine inverse. Sine inverse doesn't exist. Vectors you cannot divide. Please tell me if you have any questions. Don't hesitate. Sorry, I think I shouted. But still. Okay.
No, sir.
Next. Now I want us to define Hilbert space. Please give me Hilbert space. Proceeding ahead. Number 1. Hilbert space is a linear vector space. It means whatever rule that we studied for linear vector space are valid. Now listen. Linear vector space is something, whatever you learned until linear vector space, like until right now before Hilbert space, you have already learned probably in your second year mathematics, if you have taken mathematics in your second year, that you study that in linear algebra. However, Hilbert space is something which we learn in quantum mechanics. Okay. So Hilbert space, first of all, it's a linear vector space. It means whatever rules that were valid for linear vector, all are valid for Hilbert. And hence I taught you linear vector exclusively. Even though it's not a part of physics, it's a part of linear algebra. But Hilbert follows linear vector space. But second important rule is that a Hilbert space has a defined scalar product. Don't worry, I'll explain the meaning of it. It has a defined scalar product. What is the meaning of scalar product? We'll learn. Okay. Just like people, scalar product means basically dot product in vector. If you compare this with dot product of two vectors, it is what dot product of two vectors. It gives you a scalar. No? That's it. So when you say define scalar product, okay, I think I'm listening to this. People, cross product of two vectors gives you a vector. You call this cross product. There is another name. You also call it vector product. Because product is a vector now. Product is a vector, you call it vector product. Similarly, dot product of two vectors gives you a scalar. You call this dot product. However, it is also known as scalar product. Why? Because the product is a scalar. So when you say it has a defined scalar product, remember, in vector space, how can you have a scalar product? By simply ensuring that there is dot product happening. Okay, so just like dot product of two vectors gives you a scalar, which is known as a scalar product. Take a note, please. It has a defined scalar product. You can write dot product of two vectors, product of two vectors in Hilbert space. In Hilbert space must give us scalar. That's important. Must give us scalar. That's important. It has a defined scalar product. You cannot have vector coming out. We learned, if you remember, a plus b. Addition of vectors is a vector. You learned multiply a vector with a scalar, it's a vector. We learned these rules. But important is, if you multiply two vectors, you must get a scalar. This is the third set of additional rule that Hilbert space must follow. People. Okay. Next. So you can write equivalent to dot product basically. The idea here is equivalent to dot product. And by the way, the scalar could be a complex number. Doesn't matter. And complex, see, I'm not sure how much do you know about complex. So when you say complex number, Z, which is basically a plus bi, you write. Okay, so you divide this in two words. One is a real number. Like you can say purely real. Complex number has purely real quantity. Basically, this happens when b becomes 0. No? So in that case, Z will be equal to it has only real value. It has only real value. And there is another case which is purely imaginary. Purely imaginary. Where real value becomes 0, Z becomes only b into y. There is no real value at all. A becomes 0. This is purely imaginary. And then there is a general case which is complex number itself. So you can write complex. Okay, so this is where both of them exist. There is a plus b. So complex number itself is divided in three parts: purely real, purely imaginary, and then complex. Real plus imaginary. Both. Okay. So this could be a complex number. This could be anything, either of them. Purely real, it could be purely imaginary, it could be addition of both also. Doesn't matter. Scalar is a complex number. It could be real, it could be imaginary, it could be anything. Scalar is a complex number. Okay. So when I say complex, it does not mean it cannot be real. It can be real. It can be only imaginary. It can be both. Sorry. Done, people. Next. So definition of scalar product in quantum mechanics. So how do we define scalar product here? So if an exam they ask you, find the scalar product of psi comma phi. Psi comma phi. I'm not using bracket notation yet. We'll learn bracket notation later. So right now I'm writing this. Those who have already learned bracket notation, you should know. You write this as psi phi like this actually. But okay, we'll learn that later, not now. So psi phi, this is written as integration of people, the one who is on the left, the one who is on the left, you have to write conjugate of it. And the one who is on the right, as it is, dx. If you are in 1D, d tau, if it's a 3D problem, so that obviously dx. Okay, so psi star phi d tau, you can also write psi star phi dx. Let's write 1D right now throughout until many 5-7 days at least so far, will be in 1D right now. Psi star phi dx. Psi star I have to understand it means conjugate. Psi star is conjugate of psi. Conjugate of psi. It means suppose if they give you that psi is, let's say, a e raised to I theta. What will be psi star?
A power minus I.
Minus I theta. Just you have to replace I with minus I. So whoever is on the left, that will be conjugate of it. So this is how you define scalar product. Limits they have to give you. Limits they have to give you. Okay. Next. Let's learn properties of scalar product. People
Sir, wait a minute.
Take your time. Take your time. Take breaks, no problem.
Done, sir.
No? Okay. And by the way, remember dx, dy, dz. These are coordinates. They are real. The values 3, 5, 10, 50. dx, dy, dz are real. Okay. Also, so if they ask you, for example, phi psi, the one who is on the left, that will be conjugate. Simple. So phi star psi dx. Phi star psi dx. Next. Proceeding ahead. So to start with, let's learn properties of the scalar product. Here we go. Number 1. Psi phi star is equals to phi psi. Let's check. So basically, whenever you have psi phi star, you can shuffle the order and they will be equal. So what is LHS equal? LHS is psi phi star. What is psi phi? Psi phi is integration of psi star phi dx. No? You have to take star of it. Star means conjugate of this whole value. Integration means as it is psi star of star. Conjugate of conjugate, you go back to the real. Okay? And phi star, it becomes phi star. Dx is real now. Tell me one thing. What is conjugate of 2? 2. Conjugate of any real number, it is as it is equal. Okay. Conjugate of dx equals mean. I hope you are with me. Tell me if not. Psi integration is integration. Psi star of star becomes psi. Phi star becomes phi star. Dx remains as it is. It's a real number. Real value. Dx divided. Okay. You can rearrange this. I can write this as phi star sin a into b or b into a is fine. Okay. We learned this commutative possibility. A, B, B, A. They're scalar products. People. In dot product scalar products, a into b can be written as b into a here. So no problem. I can write this as phi star psi dx. But this definition is of whom? Phi star psi. We learned this is the definition of phi comma psi. The first one is conjugate. That's the first. Second one as it is. This is phi star psi. So I hope you understand the difference between my psi and my phi.
Yes, sir.
Okay. Tell me if there is any confusion. So LHS and RHS are equal. Psi phi the whole star is phi star. Basically shuffle them. Simple. These things are going to be again significantly important later on. But today's lecture, you don't have to take it heavily. You just have to pass through it and ensure that in the class you understand it. Beyond the class, forget it. Okay. In the class, understand it. Basically, there should be a glimpse of these things in your head when I teach you later, so that you feel that okay, I have learned this, I have learned that. Nothing else. Proceeding ahead. Next. Okay. Second, integration of psi comma psi. If you have, sorry, what am I writing? Not integration. The value of psi comma psi, just psi people. It can be written as integration of mod psi the whole square dx. Let's understand why. Okay. LHS. LHS is what? Psi comma psi. Both are same vectors. Huh? Both are same vectors. So answer should be integration of psi star psi dx. So they are saying that mod psi square is psi star psi. Let's check now. Let's do one thing. Let's define. Suppose this is a complex number a plus bi equal. Okay. What will be psi star a minus bi? Okay. Let's calculate psi star and psi. So what do you have? A plus bi into a minus bi. Okay. So a into a minus bi plus bi into a minus bi. So a into a is a square minus abi plus a into bi minus b square I square. Please tell me if you have any questions anywhere. So we have psi star psi which is equal to a square minus abi plus abi gets cancelled minus b square. What is I square, people? Minus 1. I is under root of 1 minus 1 now. So yes. I square is what? Minus 1. Okay. So what do you have? A square plus b square. This is psi star psi. What is the magnitude of this? Under root of a square plus b square. Okay. So what will be magnitude square? A square plus b square. Magnitude square is a square plus b square. This is also a square plus b square. So I can say this is magnitude square. That's it. Psi star psi is mod psi square, people. This is mod psi square dx. RHS. I hope you understood this. Tell me if not. Maybe if you have learned complex numbers, in there you learn this. You learn that z star z is mod z square, people. Okay. This can also be written as z star. Order doesn't matter. Answer will be same. Take your time, ask me if you have any questions. Don't hesitate.
Done, sir.
Okay. Okay. Proceeding ahead. Let's learn the third property. Tell me if you have any questions. How many times should I say this? Okay. So we have psi of a phi. It can always be written. Now listen, this is something which does not come naturally to a student. I would tell you throw a outside. You know, like if you haven't learned how a can be thrown outside, it becomes difficult to write this. A normal intuition for you would be, so we can throw outside and we have a both the times now. No, people in that case actually would have thrown a square outside. So to understand this, that you can throw basically when you have a vector, when you have a scalar multiple of a vector, you can throw scalar outside. To understand this, we have to prove it. Let's check LHS. Integration of psi of a phi. Sorry, psi of a comma phi. What is this, people? First one is conjugate. Second one is as it is dx. Now I can throw scalar outside now. Integration of psi star phi dx. But what is integration of psi star phi dx? Psi phi. Convincing? Simple. Make no. These things go a long way later. Like when they will ask you, for example, find the scalar product of the third wave function in 1D harmonic oscillator with fifth wave function, whatever. Or they have given us something like find psi1 is psi1 comma 3 psi 5. The first thing you can do is throw 3 outside and calculate psi1 psi 5. Nicely, plus. Okay. Anyway, next. However, trick here is important thing to understand here is, remember I already told you that scalars are also complex here. Scalars could be complex. So when we write a psi comma phi, you can throw a outside, but now it will become a star. If scalar is on the right, it remains a. If it's on the left, it will become a star. Why? Because we know the rule people. LHS is what? A psi comma phi. So when you calculate, it is conjugate of the first people. So it is conjugate of this. And second as it is and dx. And remember, this can be complex. A can be complex. I have told you that. So in that case, you have to write a star, psi star, phi dx. Now you can throw a star outside. What do you have? Psi star, phi dx. And what is psi star, phi dx? That is psi phi people. So whenever you have constant on the left, you will throw a star outside. If you have constant on the right, you will throw a outside people. Copy, ask me if you have any doubts.
सर अगर लेफ्ट में ए रियल होगा तो
रियल होगा तो टेंशन नहीं है, ऑटोमेटिकली विल रिमेन एज इट.
अच्छा तो अगर कॉम्प्लेक्स होगा तो ही कंजुगेट बाहर जाएगा.
नहीं, listen, the thing is, even if it's real, you write conjugate, that doesn't matter. Like suppose you know that value of a is 2, you write 2 now, 2 star, and then you know the answer is going to be 2. So
Yes,
you will always take 2 outside. Even if it is real, you will take conjugate outside always. If it's real, it will automatically become real. So don't worry. Always take conjugate outside.
Yes.
No problem. Done, people. Next. Okay. So suppose you had both. You had let's say something like a psi comma b phi. Now you know the answer. If you throw a outside, a star, and if you throw b outside, b psi phi. Tell me. I hope you don't need me to prove this one now. Okay.
No, sir.
Good. Next. So whenever you throw it from left, it will be star. Throw it from right, it will remain average. Next property. What is the property number 3? And then 3 maybe have learned different. 4. Okay. So psi of phi 1 plus phi 2. Psi of phi 1 plus phi 2. This can be written as psi phi 1 plus psi phi 2. Distributed people. Psi phi 2. Okay. Let's check. See, my 1 and comma could be confusing. This is comma. Okay. This is comma. And this is comma. Okay. So psi comma phi 1 plus phi 2. This is psi comma phi 1 plus psi comma phi 2. Let's check LHS. So LHS is psi comma phi 1 plus phi 2. So what do we have? Integration of psi star of phi 1 plus phi 2 dx. Okay. We can split them. So this is psi star phi 1 dx plus psi star phi 2 dx, which is nothing but psi star phi 1 is psi phi 1, psi star phi 2 is psi phi 2. I hope you are slowly gaining confidence in this. Tell me if you have any questions. Okay, done. So try to solve this directly without proving. Like you can take some simplification steps. Psi of a phi 1 plus b phi 2. This is comma. Okay. Try to simplify this without using integration. So first I can apply distributive psi of psi comma a phi 1 plus psi comma b phi. First distribute. And now you can throw constant outside. From right side doesn't matter. Okay. And from right side again doesn't matter. That's it. This will be your final answer. Tell me if you have any questions. Okay. Be honest. Hang on. I don't have more examples in this, but I'm thinking if I give you
Sir, previous slide.
sure, okay.
Done, sir.
So let me just check one thing. Don't copy it now. Don't copy. Just a minute. Psi plus psi 1 plus psi 2 comma phi. Just making integration of psi 1 plus psi 2. Don't copy. Phi dx. So psi 1 star phi plus psi 2 star phi. Okay. So here also you can apply distributive. Obviously, here also you can say this can be written as psi 1 comma phi plus psi 2 comma phi. I just wanted to check just in case there is no discrepancy in this. Okay. You can again solve and check integration of psi 1 plus psi 2 the whole star into phi dx. So this becomes psi 1 star plus psi 2 star. Psi 1 star plus psi 2 star integration of into phi dx. And now we can split it. Psi 1 star phi dx, psi 2 star phi dx. Psi 1 star phi dx plus psi 2 star phi dx. And you get this. Psi 1 star phi dx is this. Psi 2 star phi dx is this. So here also distributive is valid. Okay. Any questions, anyone? Okay, shall we? Let me try.
Okay.
7. Suppose if I would give you a psi 1 plus b psi 2, comma a phi 1 plus b phi 2. Okay. One thing at a time. Okay.
ये
So
स्टार आ
let's-
जाएगा सर.
but यहाँ पर भी वैसे a है ना, so we have to take care. A lot of things are happening. So one thing at a time. Let's first distributive this people. So we have got a psi 1 plus b psi 2. Apply distributive to the first term. Okay. Comma of a phi 1, comma of a phi 1 plus a psi 1 plus b psi 2, comma of b phi 2. I've applied this term with this plus I've applied this term with this. Distributive only to distributive of the first to the first and second term respectively. Tell me if you have any questions. Now again you can apply distributive people. This into this plus this into this. Okay. It's like bracket only. So you have a psi 1, comma a phi 1 plus you have b psi 2, comma a phi 1 plus again this into this plus this into this. So you have a psi 1, comma b phi 2 plus b psi 2, comma b phi 2. I hope I've written everything correctly. Too many notations. A psi 1, a phi 1, b psi 2, a phi 1, a psi 1, b phi 2, b psi 2, b phi 2. Okay. So from here, if you show a, it becomes a star. From here, if you show a, it becomes a. You have psi 1 comma phi 1. You have psi 1 comma phi 1. I hope you are with me. From here, if you show b, it becomes b star. From here, if you show a, it becomes a. You have psi 2 comma phi 1. Then from here, if I show a, I have got a star. From here, if I show b, it remains b. I have got psi 1 comma phi 2. And again, from here, if you show, you get b star. From here, if you show, you get b, you get psi 2 comma phi 2. By the way, a star a can be written as mod a square. Don't forget. I taught you this. Z star z is mod z square. So you can write a star a as mod a square, and you can write b star b as mod b square. Probably that would be one of the options. Copy these. Take your time, ask me if you have any questions. Don't hesitate. Done, people. See, if you are thinking, but sir, how these could be asked as in how exactly they will ask us these questions. It could not always be that what is the simplification of this. Huh? A good numerator on this we can always create. Like, let me think. For example, they're asking you find the value of this. Okay. Given that chi I, chi j is equals to 1 is equals to 0 for I equals to j for I not equals to j. Okay, they have given you this. Well, I are nothing but vectors. So basically, you can say psi comma phi they belong to chi. So chi are nothing but vectors. Okay, same vectors. Okay. And they have given us this, and they have given us that the value of mod a is, let's say, 3, and they have given us, or suppose mod a is not 1, suppose they have given you a is 2 plus 3i, they have given you b, which is 3 plus 3 minus 2i. Just writing something. Okay, how to solve this? Same question. I'm asking you to find this. If you want to write out, create a question here. Find this. Write down. Find this. Find this. And they have given you this. Okay. It's not difficult, to be honest. It's just language is not comfortable with you right now. Solution is very pretty simple. Okay. First of all, when you say psi I comma psi j is 1 for I equals to j, what does that mean, people?
Phi 1 into
No,
phi 1 and
so basically any of them could be like I and j, they should be equal. Okay, so you can have, for example, you can have psi 1 comma psi 1. This is also 1. Psi 1 comma phi 1. This is also 1. Psi 1. Wait. You can also have phi 1 comma phi 1. This is also 1. Psi could be anything. First of all, psi could be anything. Psi could be not psi. What do we call it? Chi. Chi could be anything. Chi could be psi. Chi could be phi. Okay. So you write psi. You write psi phi. You write phi phi. You write whatever you want. Chi could be anything. But if I and j are equal, if they are 1 1, if they are 2 2, if they are 3 3, if I and j are equal, then the value is always 1. I hope you understood this. I repeat. They have mentioned that chi could be anything. Okay, so you can have psi comma phi, you can have psi comma psi, you can have phi comma phi, you can also have phi comma psi. And if I and j are equal, like 1 1 or 1 1 1 1 1 1 or 2 2 2 2 2 2 2, all of them will be always 1. Their values will be 1. Their values will be 1. But they have mentioned that if they are not equal, then the answer is 0. I'm just giving you the condition. If they are not equal, then the answer is 0. So if you have 1 2 combination people, if you have 2 1 combination, or if you have 1 3 combination, 2 1 combination, then the answer is 0. I hope that's clear. Okay. So if you apply this in the final result, what do you get, people? So here I'm going to get a star a is mod a square, by the way. Okay. Psi 1 phi 1, this will be 1 now. Both are 1 1. Psi 2 phi 1, this will be 0. Psi 1 phi 2, this will be 0. Psi 2 phi 2, both are 2 2. This will be 1. What do you have? 0 plus 0. B star b, that's mod b square, and psi 2 phi 2, that is what people want. Tell me if you have any question in this. As far as the numbers 1 1 2 2 are same, the value will be 1. That's what they mean here. That is the meaning now. I and j. If as far as these two are equal, answer will be, you can say 1. And if they're not equal, answer is 0. See, I have actually given it very Huma here. I could have given it like this. Hang on. Order is always psi phi. Wait, I'll make it simpler for you to avoid confusion. Sorry, I cannot use this eraser. There is no reason eraser. Wait, you write it this way. Change the question for more, not this pen. Have to use this pen. Psi I comma phi j. I think now this is better.
Yes, sir.
Okay. So I and j, they are equal. Psi 1 phi 1 or psi 2 phi 2. Answer will be 1. If they are not equal, answer will be 0. Change the question. This is more better. And this is how actually they will give an exam. They won't give it the other way around the way I gave it before. That would be a bit confusing. Debatable also. So it's better this way. Okay. So what will the answer, people, now? I hope you understood this. Okay. So psi 1 phi 1 is 1. Psi 2 phi 2 is 2. These two are 0. Our answer is just mod of a square plus mod of b square. And that's it. Mod of a square plus mod of b square. Calculate. What is mod a, people? Mod a is under root of 2 square plus 3 square. That's under root of 4 plus 9. That's 30. What is mod b? Under root of 3 square plus minus 2 square. This is again 9 plus 4. This is again under root 30. This is mod a square plus mod b square. Okay. So 13 plus 30, answer is 26. A good NET equation we created right now. Nothing like this exists in any of the book. But I wanted you to understand the application of what we just learned. I hope you understood this. Tell me from it.
for sure. Understood.
Good. Yeah, tell us with voice volume so that I also feel good. Next. Proceeding ahead. Any doubts, people? Anyone until here? No doubts. So, do you want to say something?
No, sir, no doubt.
Okay. Are you listening in speaker? I hear my own background myself. Okay. 8. Proceeding ahead. So this we already have learned, by the way. The value of psi comma psi is integration of mod psi square dx, like we know. Okay. Tell me one thing. Mod psi square, this will always be greater than 0 or equal to 0. It cannot be negative. It's square. And magnitude, you have calculated the magnitude already at the root of x square plus b square. Okay, so this term is always greater than or equal to 0. This is anyway real, people. Answer is going to be what? Greater than or equal to 0. The integration value of this is always going to be greater than or equal to 0. Make a note. So the value of psi comma psi is always real and positive. If you basically take a scalar product with itself, if you take a scalar, what did I say? If you take the scalar product of a vector with itself, answer is always greater than or equal to 0. In English, I write, if we take scalar product of a vector with itself, answer is always greater than or equal to 0. Answer is real and positive. Okay. Remember, whatever we learned, again, that would be a good part of an MSQ. Which of the following are correct properties in a Hilbert space? And this can actually make a very good point, a C point or a D point or a P point. Okay. Answer is always real and positive. Clear, people? You can always compare scalar product with dot product I have told you. So suppose even if you have a vector which is negative, but if you take the dot product with itself, you will get rid of negative. Minus 2i cap into minus 2i cap. What will happen? Minus minus becomes plus, I dot I becomes 1, it will become 4. It will always be real and positive. Scalar product can be compared with dot product, what I already do. So answer will always be positive. Doesn't matter even if the vector is negative, answer will be positive. Okay. Proceeding ahead. Give heading. Linear dependence and independence. I hope so far you are understanding things nicely, smoothly. Maybe a bit new, but I hope there are no questions. Okay. So you have learned these things also, I'm sure, again in your BSc, but maybe you have learned the definition. I don't know if you understood the meaning of it. Let's try to understand that today. So suppose, people, if you get an equation, don't write anything here. I need to explain this. If suppose you have an equation, a1 psi 1 plus a2 psi 2 plus dot 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 plus an psi n is 0. Okay. If you have an equation like this, then psi 1 comma psi 2 comma psi n are called linearly dependent. See, the problem is you may have learned this. What is the meaning of this word? Let's understand. Hang on. People, y equals to mx plus c. This is a linear equation. Linear means what? Order should be 1. Simple. This is actually the same thing, written in a different way. So, for example, if you have learned probably in your linear algebra that a1 x1 plus, I think you were using C probably. C1 x1 plus C2 x2 plus dot 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 plus Cn xn. If this is 0, you call this as linear dependence. Like all are linearly dependent on each other. Each of the vector are linearly dependent on each other. So, what is the meaning of this? Well, it only means, take a simple example. Suppose I would give you, let's say, 2x1 plus 3x2 minus 4x3. This is 0. Suppose when you say all are linearly dependent on each other, what does that mean? Let's understand. It only means 2x1 is throw them on RHS minus 3x2 plus 4x3 throw 2 on RHS. x1 is minus 3 by 2 of x2 plus 4 by 2 of x3. That's it. x1 depends on x2 and x3 linearly. Do you have square here? Do you have cube? Do you have log? Do you have sine? Do you have trigonometric function? Anything else? No. You just have power 1, people. It's like y equals to mx plus c in 2D. So this is a 3-dimensional equation, whatever. But at the end, x1 depends on x2 and x3 linearly. But similarly, you can keep x1 on right side and throw x1 and x3 on right side now. And x1 left and throw x1 and x3 on right side. x2 will depend on x1 and x3 linearly. Similarly, x3 will depend on x1 and x2 linearly. That's it. This is the meaning of linear dependence. So whenever you have an equation like this, I think I will keep this. Oh, Control Z, Control Y, gone. Good. Oh, no, I think I can still have it. Wait, there is the next page. Let me click on this. Control Y. No, not possible. Yeah. Okay, so I was saying that so when you write it like this, it means any vector can be written as linear combination of any other vectors. People, you can always write, for example, here I can write a psi 1 is equal to, sorry, a1 psi 1 is equal to minus a2 psi 2. I'm showing them on RHS. Minus a2 psi 2 minus a3 psi 3 minus dot 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 minus an psi n. It means psi 1 is nothing but minus a2 upon a1 of psi 2 minus a3 upon a1 of psi 3 minus dot 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 minus an upon a1 of psi n. You can say this is, what does this mean? It means psi 1 is a linear combination of psi 2, psi 3, and psi n, or you can say psi 1 depends linearly on each of them. Simple. Psi 1 is linear combination of psi 2, psi 3, psi n, people. Okay? Or you can say psi 1 depends linearly on each of them. Psi 1 depends linearly on each. Similarly, all will depend linearly on each. Take a note, please. The idea of linear dependence, it can beautifully be used in a matrix also. Like if you have 3 rows, row 1, row 2, and row 3, and if row 3 can be written as linear combination of 1 and 2, it means rank reduces people. You can delete row 3 because row 3 can be written as linear combination of 1 and 2. Now, what does that mean in matrix operations, people? When you write 3 rows, I repeat, you are allowed to do operations. Now, you are allowed to write R3 as 3R3, correct? You are allowed to write R3 as R3 minus R2. You are allowed to do all these operations, right? Okay, so if R3 is linear combination of this and this, what does that mean? R3 can be expressed completely in this and this form. It means you can simply delete this row. So that way the rank reduces. No? If rank was initially 3, now it simply becomes 2 people. Very simple. Okay. So like if I would have given you suppose 1, 2, 3, suppose 2, 5, 6, the same. No? And wait, I need to explain this 1, 2, 3, 2, 3, and suppose minus 1, 2. Okay. Now I'm going to create a matrix such that this is 3, suppose this is 5, and this is 1. It's quite evident that the third row is linear combination of first and second. Now look at this. 1 plus 2 is giving me 3, 2 plus 3 is giving me 5, minus 1 plus 2 is giving me 1. It only means, people, I cannot have rank as 3. Rank will become 2. This row can be, you can simply make this row 0, people. You can simply make this row 0. How can I make this row 0? By simply subtracting R1 and R2 from it. Or you can say R3 is nothing but R1 plus R2. R3 is linearly dependent on R1, R2, linear combination, type of linear dependence. Okay. It could also be 2 R1 and 3 R2. You always have to check the linear dependency. That way you can get rid of this row completely and rank reduces. Okay. So this linear dependence idea is very handy if you know how to apply it. I don't know how exactly you calculate rank, but this is the best way. Done, people?
Yes, sir.
Shall next. Proceed. Achha, it's important that these constants are non-zero. If they become zero, what does that mean? Write it, write down. Provided that a1, a2, an are non-zero. Write down. Provided that a2, a1, a2, an are non-zero. Then Psi1, Psi2, Psi are called linearly dependent. Provided that a1, a2, an are non-zero. See, so suppose if I have given you, let's say, a1x plus a2y plus a3z is 0. Right now, x, y, z are dependent on each other. But even if the constants will become 0, suppose a3 is becoming 0, what does that mean? Now x only depends on y now. Z does not. Z is independent. Z has become independent completely. X depends only on y. So, and hence you have learned the definition of linear independence also. I'm sure in linear independence, what is the condition? If you want all the vectors to be linearly independent of each other, if you want all the vectors to be linearly independent of each other, constants should simply become 0. That way, none of them will depend on each other. That's it. So you can say if again that thing happened. Let me see if I can escape this out. See, this has become a I cannot do anything. Escape. Okay, I got this, but let me check on Zoom. No, is there an option to close all windows? This happened. Okay, let me stop the share just a second. I have no idea why it happens. Okay, not much of an inconvenience, but sometimes our things get deleted. Okay, let me check the last page. Where were we? I had written linear independence. I've lost that part, but that's okay. Let me share the screen. Here we go, people. Linear independent. Wait, I have a small idea. Let's do this. Apply this. Okay, linear independence. So, if in an equation like a1 psi1 plus a2 psi2 plus dot 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 plus an psi n, in college books they directly write a1 a2 n should become 0 and they become linearly independent. This doesn't help people. We should take it slowly. For example, if we say if a2 is 0, what does that mean? After a1 psi1, you have a3 psi3 because a2 has become 0 now, and then you have a4 psi4, and then you have an psi n. This is 0. Now it means that psi1 is linearly dependent on 3, 4, and n, but it is not dependent on 2. So now I can say psi1 is linearly dependent on psi3, psi4, psi3, psi4, and psi n. However, you can say that psi2 has become linearly independent. Psi2 has become linearly independent. It is not a part of the relationship. Psi2 has become linearly independent. So similarly, if you don't want any of the vectors to become linearly independent, it means the relationship between them cannot exist. It means all the constants must be 0. The relationship between them cannot exist. People. So you can simply say if all the vectors were to be independent, if all the vectors, like similarly, you said that if a2 becomes 0, similarly a3 will become 0, psi1 will not be dependent on psi3. Psi4 will not be dependent on psi3. Psi won't be dependent on psi3. They have lost their dependency, the relationship with psi3, only because a3 has become 0. That does not mean wave function does not exist. People. Psi3 still exists. Just that the relationship that they have with a3 that they have lost. Okay, so all of them have become independent of psi3. Simple. And similarly, I can say all the constants. If all the constants, I can say C1, C for A1, A2, whatever you call it. A1, A2, An becomes 0. Then you can say the vectors psi1, psi2, psi n all are linearly independent. Copy from here. Ask me if you have any doubts. Don't hesitate. Yes, sir. Okay. Done, people. Next, please give me basis of a vector. Basis of a vector space. Okay. So you can say that some vectors, for example, phi1, phi2, phi n, phi1, phi2, phi n, will form basis of a vector space. Phi1, phi2, phi n will form basis of a vector space if phi1, phi2, phi n are linearly independent. However, all the other vectors. Okay, copy this first. Wait, hang on. Copy this. I'll explain this. This copy. Phi1, phi2, phi n will form basis of a vector space if they are linearly independent. So you know the meaning of linearly independent. They personally don't have a relationship between them. All of them. Among them, there is no relationship. Like a1 phi1 plus a2 phi2 plus dot 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 plus an phi n, this will be 0. Among them, they don't have any relationship, and all the constants will be 0. If relationship exists, then it's dependent. You have mentioned independent. So the point is, if you want to write this, then automatically all the constants has to become 0. A1 will be 0, A2 will be 0, An will be 0 because they don't have a relationship with each other. They don't have a relationship with each other. Yes, sir. Okay, next. However, all the other vectors of the vector space, of the vector space can be uniquely expressed as linear combination of these basis vectors. Okay, so all the other vectors that you might have, let's say psi1, psi2, psi3, you can individually write psi1 as, you can express psi1 as linear combination of these basis vectors, people. So you can use any of the vectors you want. You can write a1 phi1, for example, plus a2 phi2. You can express them basically. You can express any other vectors as linear combinations of these vectors. But phi1 and phi2, all of them together they cannot have a personal relationship with each other. Together, all of them will never have a relationship with each other. Okay. Similarly, psi2 can also be expressed as like b1 phi1 plus b2 phi2. Okay. Similarly, psi3 can also be expressed as you can write c1 phi1 plus c2 phi2 plus c3 phi3. You can use whatever letters you want. How many variables you want. Here also you can write, for example, directly a4 phi. So you can express them as linear combination of the individual basis vectors. For an example, the best way I can explain this is just a second, last thing. The best way I can explain our basis vector to you is by taking numbers. See, in the decimal world, people, 0 to 9 are our bases. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are our bases, actually. What is the meaning of bases? They personally don't have a relationship between them. Okay, 8 is 8. You cannot write 8 as anything. Okay? Like all of them together, you cannot ever say that all of them together will become 0 as such. However, what we can do is we can express all the other vectors, all the other numbers as linear combination of them. So suppose if I want to express 13, if I want to express 18, I can do that. For example, I can write 13 as 1 into 4 plus 1 into 9. I have expressed 13 as linear combination of two of the basis vectors. I can express 18 also, like with the help of anything. I can write, for example, 2 into 2, which becomes 4. I can write 5 into 2, which becomes, or let's say 2 into 5, anything, 2 into 5. So
7.
this is 10 and this is 14, and then what do you want? 1 into 4, whatever. So at this way you can have it. The point is you can express any other vectors as linear combinations of these individual vectors. Okay. New things for you, but I'm going to. So let's stop here. We'll continue from here in tomorrow's class. Thank you so much.
Thank you, sir.
Thank you, sir.
No problem.
Thank you, bro.
Thank you, sir.
No problem. Shall I end session with you?